Here we're going to look at bending. Okay, so we've got a beam along an axis. I've got some sort of bending moment applied to it, causing, bending to occur. And what I mean by bending is when we have bending, for example, in this, the top side is actually being compressed, whereas the bottom side is actually stretching out. Now, there is a point on that axis where there's actually no strain going on. We call that the neutral surface, which is in line with the neutral axis if you look at the cross section of the beam. And again, no strain is going on there. One side will always be in compression. One side will always be in tension. Okay. So what we're going to do is we're going to look at a small piece that has a thickness of delta x in there, and you're going to have a piece kind of like this. Okay, that has a radius of curvature of r to what we're calling our neutral axis, which is right here. Okay, and then we're actually looking at the strain as a function of the distance away from that neutral axis. Okay, so what I have here again is my strain is this delta s prime minus delta s over delta s. Well, delta s and delta x are the same but for a strain, right? Delta s is the unstrained position. So that's actually what delta x is, because again, no strain is going on right here. Okay. So delta s prime is rho minus y times delta theta. Again, this angle. Okay. Getting the arc length of this sine. Okay. And delta s is going to be rho times delta theta. Again, getting that delta x right there. Okay. Well, what happens here is the rho delta theta goes away, and I'm left with y over rho, negative y over rho. And that's the strain of an element at some position y away from the neutral axis. Okay. Now, comparing that to what my maximums would be, so again, my neutral axis where there's no strain, my strain increases linearly as y increases up to a maximum, which is, again, some point C away, and that's basically the furthest distance away from the neutral axis you can get. Okay, so my maximum strain is that C over rho. Okay, and then relating the strain at some random arbitrary y away from the neutral axis. Okay, and comparing that to the maximum, I get a relationship like this. Again, it's a linear relationship between the strain at some arbitrary point and the maximum strain. Okay, now using Hooke's law and knowing that stress and strain are related by Young's modulus, if I take Young's modulus, on both sides, it goes away. Anyway, my stress is also related by the same factor because of Hooke's law, and we've talked about that previously. Okay, so here's what I'm looking at as far as stress goes, right? So I've got my cross-sectional area, I've got my moment, so I've got some forces on the top, some forces on the bottom going in the opposite direction. I'm going to look at a tiny little element dA here, and the force on dA is just going to be the stress times that dA, and that's what dF equals. Okay, and for static equilibrium to occur, the sum of all of these forces, therefore the integral has to equal 0. Okay, well, I know stress is YC sigma max times dA. Okay, and what I have here is sigma max and C. Those are both constants. C is, again, the distance away from the neutral axis and the maximum distance away from the neutral axis. And sigma max, well, it's not, yeah, well, they can't be 0, essentially, is what's going on here. I guess that is also a constant. It's the stress way up at the top here. Okay, but those can't be 0 if I have a moment going on here. So what has to be 0 is this integral of y dA, which is the centroid, right? So that basically tells us that I know that no strain happens at the centroidal axis. So an axis that passes through the centroid, there's no strain going on in there. Okay. Now, in order to figure out exactly what that stress is, I'm going to sum my moments. Okay. And the moment that I have here is this applied moment. That's what I've got going on here. So what I'm going to do is I'm going to take, my y distance times dF, right? That's a moment arm times a force. Okay. And of course, dF, just like before, equaled sigma dA. And going through similar things, plugging in for sigma, y over c sigma max. Okay, pulling out sigma max over c, I'm left with the integral of y squared dA. And hopefully you remember back from statics that that function right there is the area moment of inertia I. So I can calculate the maximum stress due to a bending moment as that bending moment times the furthest distance away from the neutral axis divided by the moment of inertia. And again, this is the equation. This is called the Flexure Formula, and this helps us determine, based on bending moments, what the maximum normal stress is in my cross-sectional area. Now, I could also do it for some arbitrary point y away. Okay, but again, generally, we're most interested in the maximum stress. Now, the other thing I want you to notice is this negative sign. It's not here. Again, what's more important, I believe, is to look at it and figure out, okay, well, looking at it, where is the compression? Where is the tension? And again, by our sign convention, a positive stress is a tensile stress, and a negative stress is a compressive stress. So again, this boxing equation is called the Flexure Formula, and that's how, from a bending moment, I can figure out the normal stress in a cross-sectional area.